The noble gas
6,
atoms.
Section 2. At the end of this video, I hope that you can state the octet rule and list the 6 basic steps used in writing Lewis structures. The octet rule. Unlike other atoms, the noble gas atoms exist independently in nature. They possess a minimum of energy existing on their own because of a special stability found in their electron configurations. This stability results from the fact that, with the exception of helium and its 2 electrons in a completely filled outer shell, the noble gas atoms' outer s and p orbitals are completely filled by a total of 8 electrons. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. Such bond formation follows the octet rule. Chemical compounds tend to form so that each atom, by gaining, losing, or sharing electrons, has an octet of electrons in its highest occupied energy level. Let's examine how the bonding in a fluorine molecule illustrates the octet rule. An independent fluorine atom has 7 electrons in its highest energy level, that is 2s2, 2p5. Like hydrogen atoms, fluorine atoms bond covalently with each other to form diatomic molecules, in this case F2. When 2 fluorine atoms bond, each atom shares one of its valence electrons with its partner. The shared electron pair effectively fills each atom's outermost energy level with an octet of electrons, as illustrated in Figure 6.9a on page 169 of your text or on the screen now. Figure 6.9b on the screen now shows another example of the octet rule in which a chlorine atom in a molecule of hydrogen chloride, which is HCl, achieves an outermost octet by sharing an electron pair with an atom of hydrogen.
The noble gas atoms are the only ones that exist readily in an isolated state in nature. The outer s and p orbitals of these elements are completely filled with electrons, 8 in most cases and 2 in the case of helium. As a result, these atoms have low potential energies and stable electron configurations. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. In this way, each atom has a stable noble gas type structure. Let's look at this same combination of atoms using orbital notation. If we join the unfilled orbitals of 2 atoms with a box, we see that the combination fills the orbital. There are, however, some exceptions to the octet rule. The most important ones relate to the elements hydrogen and boron. Hydrogen forms compounds to share a pair of electrons, filling its s orbital. Boron has only 3 valence electrons, and so forms compounds to share 6 electrons, filling its s and 2p orbitals.
Exceptions to the octet rule. Most main group elements tend to form covalent bonds according to the octet rule. However, there are exceptions. As you have seen, hydrogen forms bonds in which it is surrounded by only 2 electrons. Boron, B, has just 3 valence electrons. That's 2s2, 2p1. Because electron pairs are shared in covalent bonds, boron tends to form bonds in which it is surrounded by 6 electrons. In boron trifluoride, Bf3 for example, the boron atom is surrounded by its own 3 valence electrons plus 1 from each of the 3 fluorine atoms bonded to it. Other elements can be surrounded by more than 8 electrons when they combine with the highly electronegative elements fluorine, oxygen, and chlorine. In these cases of an expanded valence, bonding involves electrons in d orbitals as well as in s and p orbitals. Electron-Dot Notation. To keep track of valence electrons, it is helpful to use electron-dot notation. Because, as we have just seen, covalent bond formation usually involves only the electrons in the atom's outermost energy levels, or the atom's valence electrons. To keep track of these electrons, it is helpful to use electron-dot notation. Electron-dot notation is an electron configuration notation in which only the valence electrons of an atom of a particular element are shown, indicated by dots placed around the element's symbol. The inner shell electrons are not shown. For example, the electron-dot notation for a fluorine atom can be written by the symbol for fluorine, F, surrounded by 7 dots, each representing its 7 valence electrons. In general, the element's number of valence electrons can be determined by adding the subscripts of the element's noble gas notation. In this book and in this course, the electron-dot notations for elements 1 through 8 and their valence electrons are shown on figure 610, which is on page 170 of your text or on screen now. We will use electron-dot notation as a foundation for drawing Lewis structures. Drawing Lewis structures follow a simple set of steps as follows. Step 1, gather information, meaning draw a Lewis structure for each atom in a compound using the electron-dot notation. When placing valence electrons around an atom, place 1 electron on each side before pairing any electrons. Then determine the total number of valence electrons in the compound. 2. Arrange the atoms. Arrange the Lewis structure to show how the atoms bond in the molecule. Halogen and hydrogen atoms often bind to only one other atom and are usually at the end of the molecule. Carbon is often placed at the center of the molecule. You will find that, with the exception of carbon, the atom with the lowest electronegativity is often the central atom. Step 3. Distribute the dots. Distribute the electron dots so that each atom, except for hydrogen, beryllium, and boron, because they are exceptions, satisfies the octet rule. Step 4. Draw the bonds. Change each pair of dots that represent a shared pair of electrons to a long dash. Step 5. Verify the structure. Count the number of electrons surrounding each atom. Except for the exceptions to the octet rule, hydrogen, beryllium, and boron, all atoms must satisfy the octet rule. Check that the number of valence electrons is still the same as you determined in step 1. At this point, I hope that you can state the octet rule and list the 6 basic steps used in writing Lewis structures.